and but not get into the dynamic aspects. So let's talk about the static aspects of Droop and all that. And it brings up some interesting questions. But I'm going to stop there, because you all have to know what's going on in the Supreme Court. It's really, it's amazing. It's so relevant to this course. And it's, I'm surprised that Professor Majumdar didn't talk about it, because it's like, he's going on about markets and how you have to understand that as well as engineering. This is the best example of that. Okay, come on. And this is sort of fun. I don't know. So anyway, so first, let's review the governor business. And I'm not going to put these slides up right away, because I noticed that there's some. I just noticed today that there's some notational discrepancies between these slides and the book. I want to fix that before I put these online. But yes, I'm going to go over what we did last time on governors, and then talk about FERC. And this would, this is a whole course. I'm going to give a bit of history about how this came about and why it's being fought, and just all the intrigue about this. And it's just, I mean, you'll laugh your asses off when you hear about this, how this came about. It's crazy. I mean, and it's very important. It's about demand response. It's a very important resource, and it's just the arbitrariness of the rules behind it that I want to talk about. Okay, so first of all, I'm not going to give you a big recap on swing equations, just real fast. We saw this. We saw these big monster machines spinning. But it is good to keep remembering there's huge spinning machines, and they'll be around all of your lifetimes. We have these swing equations, and that's a bit of a lie. Oh, no, that's right, it is true. This m here is j times the nominal frequency, 60 hertz here. PM is a function of fuel rate. And a question I could ask you is, if the thing is spinning at 1,200 revolutions per minute, how many poles does a generator have? That would be a baby question. Because you should know this formula. You should understand that. I mean, Anyway, so about Droop. So this is just a picture of what the concern is. You see, this is in Europe. I mean, there's a 50 hertz there. And there's a fault. In this case, it was about a gigawatt. And these are simulations in different scenarios. And the frequency drops. And you notice how it drops in Europe compared to here. Look at that. I mean, it's. If you were in the lecture today, he was talking about keeping to 3.5% or 0.35. No.
Yeah, plus minus 0.35 hertz.
60. Plus minus 0.35, and it's negative that people really normally worry about. 0.35, and look at that, 50, 49.8. Not 49.98. So 49.98 would cause panic today here. And this is Europe, and then shooting down like that. And so this is this is without any Droop at all. And if you throw in Droop, you get some control. The frequency doesn't fall as fast. And this is whether or not there's wind around or not. So I'm not going to go into that. This is just, I'm not going to talk about details because it's a distraction, but basically you're trying to control that initial crash in frequency with Droop. And so, you've got this monster equations. I won't mention this again. I just want to recall that the input of the system is U. And last year I ended up using a different symbol than the book, which is one thing I'm going to change. There's a funny, but the symbol in the book is so strange, I don't know what to do. Maybe you'll all just accept it. So there's a valve position, and and they use a power term symbol for that. That's why I changed it. I don't know. But anyway, the input to these generators is the valve position in a steam turbine generator. And it does have some dynamics which we'll ignore. And then from that you get the mechanical power. But just notice the main thing here, the only thing to note is it's normalized so the DC gain is unity. So S equals 0 is the DC gain. So which means if you put in a constant, after units are normalized, the constant value 5 in eventually is stabilized to a constant value 5 out. And there's deltas missing here as well. These are all deviations. So I'm going to revise these slides before I put them up. This should all be deviations. But these are all approximations, because remember even the heat curve plots were very nonlinear. As you change the fuel input and all that, for different power values, you don't get a linear plot. So these linear approximations are always, sometimes crude. So briefly I talked about an isolated generator. It's absurd. It's very rare that you'll care about this. We're talking about a single little island with one generator. And then you have this integral control. And you notice I changed the notation here, and for good reason in a way, because if you take a control class and you look at the definition of integral control, you take an error and you integrate it to get the control input. Okay? And why do I use E instead of delta W? Because that's minus delta W. Everything's all screwed up with notation if you want to go from a control chorus to a power chorus. So E is the standard notation in a power chorus. This would be minus delta W in a power chorus. Okay. Now, there's a couple of things that you'll always see as well. It's not really linear. So what actually happens is there's a dead band, and so the frequency deviates by by some small amount, 0.05 hertz. You ignore it, and it's only when it starts to get big enough you start integrating. So there's a dead band. They add this nonlinearity. So that's something. So in reality, it's not really a linear control law. It does nothing until the frequency gets big enough and then starts integrating, which is a hard thing to analyze. And there's also this command input, which is both typical and a big part of the next lectures. The fact that the balancing authority sends a signal and the generators react. That's automatic generation control. We'll be talking about that a lot over the next weeks. And that's where a lot of the fun comes in, Okay. So, this droop curves that come in is, I say, that leads to this, I don't know. That's partly true. It's a lot of things lead to what's called the droop curve, which I'll explain now. Okay. All right. So that's nonsense. So the real generators are not like this. They're synchronous. Again, you understand why this wouldn't work, right? You all with me? In case you weren't here last lecture, the system frequency, that's a system property. All of PGM has the same frequency. And so normal notions of control don't apply. If that thing, me by one single generator, is not going to compensate the frequency of the grid by myself. And therefore, this would remain big for a long time, which would mean this would blow up, and you'd have a real problem. So this is an absurd control solution for this particular problem. So that's the thing. It's outside of the scope of any control course you'll ever take. You've got 100, 200 generators in a region, and all of them are working independently to stabilize the grid. That's a distributed control problem. There's no science for that. There's no science for distributed control. There's not a book on distributed control except for a bunch of hacks that, nothing at all. And so power systems engineers have come up with hack after hack and made this beautiful, reliable system. It's fantastic. And so what I'm describing right now is just one hack that has been magical how well it's worked. And I emphasize that because when people come in and they want to revolutionize the grid, they're forgetting nobody knows why it works so well today. So if somebody's going to run in with some fuzzy logic controller that's going to, do some magical thing, they're saying that without any understanding of the difficulties today. It's really something. So I say stiff here. Forget that crap. This is just absurd. So forget it. So what you do is instead of, I said I wouldn't use the term, but isochronous governors, what they call this, which barely exists. So don't worry about it. You stabilize it basically again. So. And again, I'm going to change the slide. Forget that. There's a signal from a balancing authority that comes in here. We won't discuss that till next week. So forget, just erase that from your memory. And you basically, you put in, I can put the minus sign there, you have negative feedback in a way to stabilize this unstable system, because integration is an unstable operation. Okay, so putting that negative feedback loop will stabilize the system. So even if that, I don't want you to see that, even if that error remains constant forever, the fact that you have that negative feedback will mean that this will not blow up anymore. That's the whole thing. And so then you get this behavior, and you can basically control the rate of change downwards by creating, designing this governor right. Right? And because of deadband, you might get a very steep behavior initially, because it doesn't respond initially to a frequency. And then it kicks in, the governor response helps you out. And it keeps helping out, but there's going to be an offset by doing this. So it's going to take a lot of time to explain how you then bring things up to the nominal frequency and all of that. So the governor is not about anything steady state beyond this initial transient period. Just trying to keep that frequency from going too low. And then some other thing called secondary control, which we'll talk about later, will kick in over here. So it's an incredible hierarchy. Again, think about the layers. I mean, first of all, you want the physical system to have nice properties. So you want there to be big, heavy spinning machines to have inertia. You want capacitor banks around to deal with the reactive power, which we haven't talked about yet. So there's all sorts of things about system architecture to get a nice controllable system. And then you have these distributed control loops. Every generator looks at local frequency, completely myopic, and makes decisions based on local measurements. And they all work together to make something happen. And then you need more and more layers of control to make the whole thing work. Now that's unique. I mean, there's two examples I can think of like that: power systems and telecommunications. And it's just like telecommunications, it was the same set of hacks. There was a big problem with congestion control once, and they didn't know how to deal with it, and it seemed like an impossible problem. And they came up with TCP/IP, which was just a completely let's try it. I won't go into much detail. And magically, they were able to tweak parameters, just very similar to this, to make users be able to communicate in the communication network and have them cooperatively reduce congestion when things get bad, and then recover like after a crisis to a good new steady state.
Do we ever find out why European systems can droop so low?
Yeah, and it's just the kinds of generators they have. So their portfolio of generators is more robust to frequency variations than ours.
Because they're modern, or
no, the opposite. So the old-fashioned generators can handle a lot of frequency variability. It's the super high-tech ones that have really tight standards.
So these have less efficiency.
They have much less efficiency, most likely.
That's a trade-off. So they must have a lot more generators than America does.
No, actually, their load is so tiny compared to us. Yeah, their load is so. I mean, you don't. People just don't have air conditioning in France, for example. Even in hot places. I mean, the load is much less. Is function of population.
Is there the slope of the system inertia? So it depends on the inertial constant.
Yeah, that's right. Well, we'll see that today. So, we'll see. The thing is that we saw D played a role in all of this, in the dynamics, and that D was the damping from these frequency-sensitive loads like motors. Droop is going to have the same role as that damping constant, exactly the same. Scribbles on blackboard. So this is tough. You know why it's tough? I was actually hosting our speaker this morning. I ran out at 6 in the morning or whatever, and I forgot my lecture notes, so I reconstructed them this morning. Not this morning. I reconstructed them mainly after the lecture in the last half hour. But it's not too bad. Let me rewrite this thing and let's play with it. So. God. Okay, so you can see why I didn't like the standard power terminology for the valve setting, deviation of the valve. P sub valve, I mean, that doesn't sound like power to me, I don't know. But it's just the angle of the valve that, letting steam into a turbine. So last year I changed it to rho v, but that's confusing as well. I should stick to the book's notation. But to me, it's U, it's the input to this damn system. Let's use power control notation. U of t is the input to the system. And I'm using control notation there, an error signal, but that's minus delta omega, because delta omega is omega minus omega naught. So omega minus 60 hertz. Okay? And usually when you talk about error in control loops, you talk about what you want minus what you've got. So there's a sign difference there. So yeah, it's just, yeah. Okay, so we should unravel this. So that's what it looks like. And let's look at there's two things we need to look at. We need to consider dynamics. And this is pretty hard. So what would you expect for this thing to be? Now, we're not going to get that from one generator. I mean, these guys are all talking to each other virtually through wires. They're all synchronous, and they're all supplying power. So one generator won't answer the question, and that's why I'm going to take maybe take a little time to explain that. But we need to somehow get a feeling of dynamics. But let's start with statics, steady state. So dynamics is all about this, all these guys working in parallel here. That's pretty subtle, but we'll get some intuition. Steady state is sort of here, which you never actually see if you look at the grid, because what's called secondary control comes in, so you can't really see it very well. But if there wasn't some secondary control that resets the frequency, this would just converge to a constant. Let's get an intuition about what that constant is. And I think that'll be useful. So let's look at it. So first thing we have to do for both these things, we need to look at the transfer function from the transfer function from a deviation in frequency to a deviation in mechanical power. And the mechanical power, energy is conserved, so deviations in mechanical power is going to go to a deviation in power consumed by somebody, assuming no losses. So let's do it. We've got a gain times an integral. But I don't like integrals. Let's replace that by 1 over s. We know the transfer function for an integration is 1 over s. So forget about integrating. Let's look at the frequency domain, or Laplace transform domain. I mean, u of s, if I take the Laplace transform, it's not a Lagrangian decomposition, it's a Laplace transform. I get 1 over s times g, kg. And I get a minus delta omega. And a minus times r times u. What's that? Yes. Yeah. Well, but not in signals and systems. Right. So you need to know that the Laplace transform integral is 1 over s. But yeah, I'm gonna go through, give a crash course on PID control. Basically, it's worthwhile even if you've had control.
I have an exam on it Friday.
So. All right.
Everything that's class.
Yeah. So no, but this is not. This is signals and systems, right?
Yes.
Yeah. Given a block diagram, how do you find it? Yeah.
Actually, they would consider this communication systems.
Really?
Yeah, signal systems.
That's crazy here.
Your example.
Yeah, that's a UF eccentricity.
Right.
But it doesn't matter. Discrete time, continuous time, it's all the same. So anyway, you go through this, and I see I've got a U on both sides, so you bring it over. It's easiest just to say, if I multiply both sides by S, I'll get I can get rid of that 1 over S, and bring the KGR on the left-hand side. Right? All right, so some algebra there. And then I can go through and I can bring this across and divide. Yep. But again, my interest was in dynamics and in steady state. And there everything gets mixed up. So if you bring out a 1 over r, so I multiply by r on the top and divide. I get a breakdown into steady state and dynamics, you know. And I mean by that is that this is a first order transfer function whose DC gain is unity. If I set S equal to 0, I get 1. That's a DC gain. Yeah. All right. You know, you plug in a frequency here, j omega, you get a frequency response at a frequency omega. One particular frequency is DC. That's J0. If I plug in 0, I get 1 over 1 is 1. Okay? So there's the dynamics, the transfer function with DC gain. There's the overall gain, a minus 1 over r. Okay? And that's the and that's tells you what. So I can kill this now. I know that the response between frequency and delta valve. It's about. What's that? Well, what I did is I said I multiplied the top by r and then I divided by r. So I get a 1 over r. But then I had a KGR and a KGR, so I just divided.
Oh, that's a key G.
Yeah, KGR, yeah. And so the reason you do this is there's a pole location at minus KGR. So 1 over KGR is a time constant. For just one generator, and it has a pole, this transfer function, at minus KGR. All right. But again, all of your control intuition, if you have any, goes out the window because these guys are all interconnected. This is not a generator operating isolation. So even though, if you really know control well, you know, you'll say, wow, that's a big pole, man, it's going to respond fast. And it's not, because it's connected to all the other generators through this coupling term omega, because that's a common delta omega for every generator in all of the eastern United States. That's what's wild, you know. That thing is the same everywhere in the US. So everybody, all the generators are like connected together through one common node. You know, it's hard to get your head around that. So control, as you know it, if you do know it, doesn't apply. You know, you've got you've got to look at them all together as a coupled dynamical system. All right? So that's why the dynamic thing is kind of hard, and you can get some intuition, but it's hard to be very precise. Steady state, no problem. If you really believe that the frequency is common, then and that we didn't make any mistakes to this analysis, and we didn't, then steady state's a piece of cake. And let's play around. Okay. So how do I want to say this? Okay, so suppose that there's a loss of load, or an increase of load. So most likely, really, we're talking about is a generator trip. So you've got a 500 megawatt generator, wham, it goes out. What happens to the grid? You know, let's figure it out. And for this, we really have to think about all these generators working together. They all have this same control architecture. Every one of them has the same characteristic. And what happens? So let's say if it were a generator really going down, we're modeling that as a load going up. It would be a frequency insensitive load if we model it that way. You know? So if that would mean, in the language we had before, okay, so we're looking at just like a constant increase in load, which is the same as a constant decrease in generation, and that PNF was non-frequency sensitive. Okay? All right. So what happens? Let's work it out. So we have to we have a whole bunch of equations we have to solve. You know? So in steady state, the frequency is going to settle to a constant value. And and it's going to, and we can guess it's going to be negative. That's yet to be proven, and maybe there's some miracle here. Something happens where this oversupplies power, and the frequency actually goes up. Who knows? Well, let's find out. But no matter what, we know that there's some power change from the frequency-dependent loads. So we know that the delta PF, as I recall, how are they related again? It's equal to D times delta omega. Right. Now that's really important because you have to look at the sum of these two guys. Okay? So so we were nominal, and suddenly now because of this increase in load, we have this new load. Now we will see this is negative, okay? So even though maybe this was 500 megawatts, this could be minus 100 megawatts, so it's something smaller. We'll see that in a minute, okay? But that new energy has to come from somewhere, and it's coming from not the valves, it's coming from the power. Okay, so suppose we have capital N generators, and there should be deltas there, yeah. Each one of them is going to change their power and to meet the new load. With me? Yeah. So what are those values? Well, we don't have a delta PM here. We have a delta valve position. But remember I made a big deal about saying we normalize things so that the DC gain between that and that was unity? So I said it a few blackboards back. We normalized it. We normalized, I'll write it down again. So if you've got a constant deviation in valve position here, then you have to look at the DC gain of this transfer function to see what's the deviation in mechanical power. Well, DC means set S equal to 0, so you get a 1 here. So when I'm looking at steady state, there's no difference between the steady state behavior between delta omega and valve position and delta omega and deviation in mechanical power. All right? Yep. All right, so you got to review your signals and systems. You know, you have a stable linear system, and you have a constant input. You compute the constant output by looking at the transfer function value at 0. That's a DC gain. In this case, it's unity. Okay? So we know the DC responds from a deviation in frequency to a deviation in valve position, and that's the same as the deviation in power. Oh, D was that, it was the, no, D, remember, was the frequency sensitive loads, you know, motors. If the power goes down, the motors slow down and they consume less power.
Right.
So all the motors will slow, you know, power consumption from frequency sensitive loads will decrease if the frequency goes down. And D is a proportionality constant.
Okay.
Yeah. So D is actually I guess the sum of all the DIs of every load is frequency dependent.
That's the rate at which general consumption is lowered due to frequency.
Because exactly, yeah, that's right, and yeah, okay.
I mean, how is the deviation in frequency the same as delta PM?
No, not frequency, valve. Right here.
Yeah, okay.
No, right there. I'm saying that since I understand how deviation in frequency affects deviation in valve position in steady state, I also know how it affects the deviation in, yeah. So in steady state, let's just write it down. So I know that for the ith generator, so it's you know, looking at steady state analysis, delta val, which is what I called U of t and all of that, is the DC gain of this times delta omega. But it's, again, setting S equal to 0, I got a minus 1 over R. And again, common delta omega, that's the system frequency. It's not the frequency of this rotating shaft. It's the system frequency. And then I've got it because, again, that tells me my delta PMI. Again, in steady state, I'll have this equation. Cool. So I've got this form. I've got 3 formulas now I can put together. I have a formula for relating the frequency-dependent loads, deviation frequency. I have conservation of energy right there. And then I have another equation that tells me that actually the deviations in power are directly related to frequency because of this clever control design, because we've used this droop control to do this. And
So delta omega changes with time?
no, it does, but when I talk about steady state, remember I showed you those curves. You know, the frequency was, say 60 hertz. A crisis happens, it drops down, it curves up, and then it reaches some new constant value. It doesn't go back to, without some other action, it won't go back to 60 hertz. And I want to find what the new value will be.
So is it time varying system? Or?
No, steady state means that eventually it's... Whenever I talk about transfer functions, we're talking about time
Wait.
homogeneous systems.
Why does it not go back to 60 again?
It does not. You'll see. I'll give you the formula.
Oh, okay.
Yeah.
All right, I was saying, because I think that doesn't kind of defeats the purpose for controls.
No. That's the thing. So this distributed control architecture has only one purpose. It's sort of it's to keep the swing of frequency to go too far, because then you're dead. Then there's nonlinear effects, all sorts of strange things we don't know.
So it's not to bring it back to the
Not at all.
frequency, but just to stop the change from being too
Too much, exactly.
Okay.
Yeah, we want to avoid any big frequency excursions. Yeah, that's the thing. I mean, that's what it's going to take. There's layers and layers of control, and it's incredibly fragile. So let's put it all together. I don't need this anymore. I've already used this because I don't care about the dynamics. I'm doing all steady state. So, yeah. So let's plug it in. I can put in there all the minus blah blah blahs there, and I can plug in this there. Let's write it down again. And you can see how nice this is. I've got each one of these is proportional to delta omega, and this guy here is a proportional to delta omega. And I get this lovely expression. A minus sign outside, I get a D here. And there you have it. Except I'd rather write it the other way, so let me do it. Okay, so if there's a jump in load of 100 megawatts, say, or a 100 megawatt generator drops out, and if you have this control architecture in place, the frequency will restabilize to a value, which, as I said, is negative, because this is a positive quantity, multiplied by all of this. And there it is. And you can see how weird this is. I mean, and now I really wonder, why was that guy in Detroit screaming about refrigerators? So he was upset because the D has gotten smaller because there's more solid state refrigerators. So there are less motors contributing to this D term. But why not? We know what N is, and we get to set the droop gains. We have a lot more authority here. Why not just go through and play around more with the R's? And I don't really know the answer. I mean, I would think that, I don't know what the whining's about. I mean, I guess generators don't like being fooled around with. They don't want this to be very big. They'd like R to be huge, so they don't have to worry about the grid. I've heard stories that they fooled around in the past and changed the sign of R because they've been told by their friends that if they make their R negative, they'll actually make money somehow. That's a rumor. I don't know if it's true, but they don't want to deal with this. So it might just be that the generators don't want to be moving up and down their power, which is does cost some money. So you'd like to make this as large as possible, and so therefore you'd like to take care of this from loads if you can. But you all got that email from me that every year NERC, the National Energy Regulatory Council has a new panic about drupa values, and they're putting new orders on what these R's should be every year or so. So it's and so anyway, but this the gain is not as important as the dynamics, and because after all, as long as it's finite, you're happy. So again, other resources have to bring it to steady state. Mainly, I'm showing you need something to bring this to steady state. You're going to have a constant deviation in frequency unless you bring in other resources to solve the problem. Yeah. Okay. Clear? All right. So so it'll be kind of fun to try to build a model for the grid, but we'll do that after we understand the control issues a bit better. That's a dynamic question. Let's take a 5-minute break, and then let's hit FERC and understand this this FERC order. What the Supreme Court's talking about right now. They're actually yelling at each other at this moment about this FERC. Yeah, at this very moment.
When they yell at each other.
Oh, I mean, God, it must be amazing. I'm doing this earlier than I thought. Yeah. So this is an amazing story. So, and yeah, I mean, it really was very, so, I sort of got back in, I started in power myself.
I got that.
Oh, later, yeah.
58,000 gigawatt hours.
Wow. Oh, that's horrifying. That is so sad. I'm sorry I asked. Oh my God, that's so sad.
I mean, at least no one got hit by it, right? It was a test, I think.
Oh my God. Oh God, I felt lightheaded for a second. 58,000, forget it. Oh, that's horrible. Anyway, so forget all this. This is text you can read later, okay?
Sorry, Bob.
So demand. This is all about demand response. Okay. So like it's been in practice in Florida since the 70s, that a hurricane's coming, shut down your pools. Okay. That's been around everywhere in the world forever. Everyone in India likes to joke. We've been practicing demand response since power first started, when we have a blackout, that's demand response. But the thing is, it's been around forever. But the thing is, there are issues about some of the. There are issues about how to compensate and whether it was fair the way it was being done. So, in 2010. There'd been a lot of lobbying by various interests to FERC, and then they finally proposed a procedure to pay demand response resources. How much should I pay you when you shut down your pool for 2 hours? And we all know the answer, right? It's marginal value, right? I mean, anyway, so. Or marginal cost. That doesn't make sense for the consumer. Right? I'm doing my optimization. It's marginal value from the. Anyway, but this is all serious. So they came up with these rules. So the ISOs and RTOs. I mean, again, I've shown you pictures. Again, these are the major balancing authorities in the United States that fall under FERC's jurisdiction, are highly regulated on what kind of market rules they can implement, and FERC decreed that they had to pay demand service providers, people shutting down their pools, at all hours, the market price, the full locational marginal price for energy reductions, and it applies to both day-ahead and real-time markets. And so this was a call for comments, and comments had to be put in. And this is very hard to interpret what the hell they're talking about. What does it mean? Think of it over. I mean, do you have any idea what it means? I bet none of you do, unless you've thought about this before. It's really hard to interpret. And I'll go through and I'll give a definition in a bit. But just remember what the definition is, that the ISOs has to pay the full locational marginal price those are the prices in these real-time markets or day-ahead markets. It's the solution to our economic dispatch problem, in all hours. Okay, and so then you look at, what's been happening since. Like this is ERCOT in 2011, when prices are normally, $40 a megawatt hour. They hit the price ceiling of $3,000, and there was hundreds of millions of dollars sucked out of the economy. This is just from cold weather, and now the price cap's $9,000. And this is on the website now. I updated the website recently, so I don't know if that's 9,000 or 5,000, but that was just a few weeks ago. Now, what the hell is that? Is that marginal cost or marginal value? What do you think? Who the hell knows? It sure isn't marginal cost of any generator that's ever been built. I mean, maybe one of those hand cranks. A CEO, Donald Trump, turning a hand crank. It's that. And so day-ahead prices too can hit these crazy values of $3,000 a megawatt hour when they should be 30. And is that marginal cost? No way. What is it? So the point I'm making here is that locational and marginal prices are such strange things. It's a very odd thing to mandate this. Okay, so that's the first thing. So the objectives of demand. So in all these negotiations and all the public discussion about what to do about this issue, how to pay for demand response, how to organize markets. Of course, they had to say what are the benefits and all of that. And here's a list that you can find. The links here everywhere. Every one of these pages has a link. You can see. So ensure market customers enjoy net benefits from demand response. That's bullet number 1. I have no idea what that means. I mean, first we have to define what demand response means. Well, it would take some time to define that. And who are the customers? Are the customers the utility companies? Are they the retail customers? What are we talking about? And what do I mean by what is DR? Well, the thing is that if you send off a signal and everyone shut off their demand, it would send a shockwave through the grid that would blow the whole thing up. So defining DR would be a really delicate thing of performance. How they respond, how they reduce their demand. Does the demand do this? Some people think that's the dream. Well, maybe not. Maybe it should be that slope would kill everybody. And also, does it do this? Now, I'll tell you, that happens in practice. There's a huge rebound effect sometimes. Now, is that demand response? If they responded, and it's a very, very strange, it's very hard to define. So the people who are talking about this could never have given a definition, and they didn't talk about it. Mitigate price formation concerns is strange jargon. It just means price manipulation, really. Forget there's some language here that none of us could understand. Ensure that adequate baselines can be maintained. They would have done it anyway. They were going to reduce their power anyway. A baseline is what would they have done if they hadn't been an opportunity to reduce power. What would they have done? That's a baseline. It's amazing. And so still people talk about baselines. How can you predict what somebody would have done? Who knows? So baselines is a huge issue in this field. And then balance between wholesale and retail demand response. I don't want to get into that, but I don't know what that means. So for the next exam, maybe you'll have to answer these questions. I'll give you another warning later, because we'll discuss this, how we would try to define this, what's the meaning of all these things. And this to me always cracks me up. It's just, it's talked about seriously all the time. How much power would you have consumed, if you were at home and not here, Anyway.
So baselines, is that referring to the price?
No, baselines of power consumption. So this is in response to a request, from the Power Authority, and the Power Authority is supposed to know what I would have consumed if it wasn't for this event. That's called a baseline.
The load forecast.
Well, you could, but the thing is that there's always going to be fights. I'm going to intentionally make my power unpredictable in a situation like this. I'm going to intentionally make my power vary. I'm going to do anything I can to game this system. I'm going to, of course I will. I'm a rational agent, okay? My load might be flat today, but it won't be, So anyway.
So is this just like heavy regulation of ISOs?
No, it's just that we'll get to that. Okay, we'll get to that. So it's basically.
Like how could you like ensure that something like that can be maintained if you're not going to do heavy regulation?
Oh, you mean you're monitoring consumers, and they do that. Yeah, they monitor the hell out of consumers. And for some consumers, it does make sense. I mean, if you look at Alcoa, when they're making cans that they're consuming 100 megawatts of energy. You can watch that, and you know that. And you can know that they produce 10% less cans. I'm joking about cans, but and so there you can get a really good contract where baseline makes a lot of sense. But when you're talking about aggregating a lot of consumers like us, forget it. I could play so many games with this. It's amazing. So So we'll talk about that a bit. Some things here. Again, this is mainly for you. So there was demand response before. I can't go through all of this, but there were all sorts of crazy rules in every jurisdiction, and that's one of the things that caused the problems. And I won't go through all these, but the one region only paid the demand, the load shedding when the prices were above a threshold. PJM would always pay, but they had some sort of offset term. California ISO even paid for reserves. They paid a capacity payment. And I guess they do today. And Southwest Power Pool, which is not an ISO until last year.
I don't know if social planners problem.
Oh, right, Southwest Power Pool. They still don't have, I checked their website, I couldn't find any mention of demand response. And again, why the locational marginal price? Before FERC 745, they decided that was the right thing. And why introduce a threshold? I don't know why they introduced a threshold. So now, how does this address any of our objectives? So I don't see how any of these issues are addressed by this formulation, but that's what's been accepted. So let's now go look at the theory in class and see what the right price should be, and just laugh a bit. So basically, historically, by the way, this was just used for contingency reserves. There's a crisis, wham, I need to shed some load. See, that, because this all started pre-fracking, pre-renewable portfolio standards. The only big issue in the grid was contingencies. A hurricane comes or a generator goes out, and I got to respond fast. The whole world has changed since this ruling was put into effect. So the value of demand-side resources are usually more important than they were 5 years ago because there's more volatility. Okay, so I'm gonna skip this. Oh no, I'm not, because the thing is that what happened was, and it's happening today, PJM kept lowering their prices that they pay. They kept on changing the rules. And so the suppliers were leaving, and so they were losing resources. Now, PJM was happy because crises weren't happening that often, so it was fine. But there was risk to society. There's more chance of a blackout without resources to deal with it. So that was one big thing there that you can find if you're on this link. And so basically, the amount of demand response is becoming so small that, and it's because compensation is not enough, and so they're not getting enough resources around, and so the arbitrariness of compensation was a concern to regulators. But I think mainly it was lobbying from interest groups who wanted to make money on this. Really, rather than anything else. But the main thing they said is that these pricing rules fail to reflect the marginal value of demand response resources to ISO RTO energy markets. But they're talking about marginal value to the ISO and RTO, not to the consumers. They're using our language, but they're using it, to the grid. It is the social planner's problem. It's marginal value, though, to society in some sense, maybe. It's weird mix of economic language. It's a misuse of language. Okay, so that's what the language they used. But so the competitive equilibrium answer, let's just go through this quickly. Recall the social planner's problem. We had this business here, and we know that the slope here is a Lagrange multiplier, and we know that's the marginal cost, don't we? No, we don't, because when the slope is that high, it can't be the marginal cost. And so that's the marginal value to consumers. It would be, it could be, if you were going to try to justify this high price, it would have to be marginal cost if this was a competitive equilibrium. That's how you'd have to think about this. But that would be really hard to think about. And that kind of discussion never came up. And forget this. I can't, it's too complex, I think.
You have 30 minutes.
What's that?
You have plenty of time.
Oh, plenty of time, you're right. Fantastic. Wait a second. Weird. Okay. Let me try to explain. So again, this is all from this very confusing plot. It's very hard to find resources that are readable. But basically, this is an example where the LMP, the locational marginal price, would have been $150. Okay? But loads reduced their chopped off some of their loads, reduced their consumption by some amount, so the new load became over here. So locational marginal price became $80. I'm confused already, because if they could all instantly drop their load, was the LMP here or here? What price do they get paid? If they instantly change, the LMP would instantly change. It's very confusing. But anyway. But I don't know why they call that the retail generation rate. Forget that plot, it's too confusing. I'm just going to go to this. Let me describe it in words. Here's how I get paid. Right now, so FERC 745 is only semi-dead. It's been allowed to keep going. And if I am in the market and providing demand response services, suppose I'm consuming, my pool's on, I'm consuming a kilowatt hour, a kilowatt of power. I shut it off. Well, obviously, if I've shut off my power consumption, I'm not paying money for electricity anymore, right? But I get paid the LMP on top of that. So I get paid, I would have been consuming a kilowatt hour every hour. For those hours I'm not consuming, I get paid this LMP. And so they screamed, that's not fair, it's a double payment. That I'm making money because I'm not consuming electricity. And on top of that, I'm getting paid this big LMP, $150 a megawatt hour. And I don't know how they get the 150, but that's how they work this out. Because they work out what the LMP would have been and what this is now and all this. I mean, it's very confusing. Yeah.
What the LMP would have, right?
Well, the thing is, yeah, I mean, this is during the that's the thing. This is just in 1 hour. It's not. It's actually the LMP afterwards. So I mean, I guess there's a delay. I don't know the exact rules, but you will get, for the first time segment, you'll get this LMP, but it'll go down. So it will change. But still, it was so. There was, after this order came in, immediately there were lawsuits, and the main argument, it was a double payment, that I'm getting paid virtually because I've turned off my pool pump, and then I get an additional payment per hour based on the LMP.
So the consumer is incentivized to not use extra demand.
Well, they're just saying it's a double payment. I'm getting paid once because I'm getting money because I'm not consuming electricity, and then getting more money on top of that.
For no reason.
Let's get to that. Thing is, so they said it's not marginal cost. I mean, the things they said were crazy. So the thing is that there's all this talk about it not being marginal cost and not being fair. Now, is that marginal cost, marginal value? It's nothing. It's a meaningless thing. We're talking about an LMP they all knew had no meaning about anything in reality. And I agree that's a ridiculous amount of money maybe to pay a consumer, or maybe not. I mean, let's just think a little bit. It could easily be marginal value. I mean, it really could be marginal value, or maybe not. It's absurd for them to pretend that they know. So all these economists came in saying they're the answer. It shouldn't be double, it should be half that, it should be this. It's totally has to do with context. I mean, it really is absurd. Just like I was saying before, shutting down Shands Hospital, marginal value is way more than that. Shutting down UF probably isn't that much for a day. It's just, we'd survive, right? They completely forgot the real consumer. There no discussion whatsoever about the consumer. It drives me crazy. So the power Alcoa has a business, and if they've got a order for some aluminum, some tubes for some military contract, and if they miss their deadline, they'll lose that military contract. The marginal value is way bigger than that. They lose. The CEO loses his job. But during soft times, they don't care. And their marginal value might be very low. And none of that came in. It's just unbelievable to me. So anyway, you pay for power for a reason. For a pool pump, of course, big deal. But for something else, it matters. So I forget all this. But this is not. So anyway, there's more discussion about fighting back and forth. They do actually admit that if you look at all the costs and benefits, it's impossible to know if it's an efficient or inefficient solution. So in some of the fights going back and forth in this, they admitted that you can't really evaluate the value of demand response. The benefits sometimes are so huge, it's incredible. So you can't tell about efficiency or inefficiency from any of this. So that's really cool. So they sort of implicitly in some of the arguments that went back and forth that the payments are arbitrary, and that's the fact. The price paid for demand response is always going to be arbitrary. Marginal value is a heuristic that we might go by, but marginal value, as we're going to see in this course, is really subtle. It's much more subtle than you think. Okay, so ENERNOC was a big player in all this. So ENERNOC was really lobbying for this, and they're the ones who were really pushing, saying that there was insufficient investment, and that we'd have this insufficient reserves of demand response. So they knew there was a big business case here, and they were also right. There's a lot of value, and so without sufficient investment, there'll be no development of these resources. And without compensation, you'll undervalue these resources. And so FERC, because of ENERNOC's lobbying, mainly ENERNOC's lobbying, others as well, they decided, okay, you're right, LMPs is it. And so the only change after FERC 745 is the big change is they put in strict rules. You must pay LMP, and that's it. And so FERC 745 was born March 15th, 2011.
So I'm just going to say this just to make.
Yeah, I know it's confusing. Yeah, it's confusing.
So you're saying that this order is saying that you have to pay. The consumer has to pay the LMP to demand response providers.
So the people who control the grid have to treat demand reduction exactly the same as generator increase. So I'm providing a service to the grid, I'm a virtual generator by dropping my load during times of need. The value of that to the grid is exactly the same as the value of a generator going up. So I guess so. I mean, why not? I mean, it's as good as anything.
So the ISO pays
Yeah, the ISO pays the consumer, which is going to be an aggregator who aggregates a bunch of loads, or a big consumer like Alcoa. Walmart is in on this. Walmart's a huge energy consumer. They sign contracts for this. And they get, in addition to not having to pay for electricity, they get paid the locational marginal price. You know.
So the ISO gets paid that amount.
No, ISO pays them to
ISO
provide the
pays
service.
The utility.
Yeah.
that-
No, the generator.
Okay, I was understanding that ISO.
Demand, right there, demand. See, ISO is the one who basically does these auctions, you know, and they,
Right.
and
They don't
basically,
generate any power themselves.
they don't generate power. They're the middle men and women between the utilities and the generators. And now it's utilities, generators, and virtual generators like Alcoa who can reduce their consumption
8 times of
in times of a need. Yep, that's right.
And then those virtual generators will get paid the marginal
They'll treat exactly.
price.
They'll get exactly the same as generators. And when you say it like that, when you're saying that a load provides the same service as a generator, why not? Of course, they should get the same price payment. You know, if what if the grid operator wants is this? I had a nominal power level pumped into the grid. I want it to go up some amount and then go down. If I get that from instead load going down, the value to the grid is the same, so the payment should be the same. That's the logic. And well, sure, why not? Well, I'll see a why not in a moment. But but in terms of, I mean, it makes perfect sense. I want to buy some raisins. I'll get my raisins. If the same raisins, I'll pay the same amount. And so the service is the same. So this issue of double payment's absurd. Sometimes it's too much in quotes. Sometimes it's too little. It's just trying to come up with the right payment is very
At
strange.
the same time, I mean, like, okay, yeah, I mean,
No.
like, so the consumer benefits because they have they don't pay for the electricity as well as they get paid.
Well, big deal though. They don't get to make their cans. That drives me nuts. I mean, we have these lights on for a reason. I mean, we have the lights on because the cost of paying for the lights to be on, is very low compared to the value of light hitting this room. So the value of electricity is more than the cost I pay. So by this logic, we should be giving the consumers more. I mean, maybe, I don't know.
Variation with like what type of consumer you want. I mean, if you're paying the marginal value.
Well, marginal value, forget all that. LMP is a fictitious thing in the grid. It doesn't correspond to marginal cost. It doesn't really correspond to anything. And if the ISO needs a service, I mean, society needs a service. Society needs that because a generator went out. It's really discriminatory to give more money to generators than other service providers for the same service. So I think in a way they were right on, if you think in the short term. Okay? But I'm going to blow this away. I'm going to tell you it's the most absurd thing you've ever seen.
There was no economic theory supporting.
There's no way you come up with economic theory to support this. It's impossible. And people pretend that they can do an economic analysis as they're just, they're just not thinking. I mean, and I can explain to you all right now. I mean, just why it doesn't make sense. So it makes perfect sense, in terms of services. I need a service. I need to pay, the lowest I can. And you could say you could have an auction, but that would be devastating too. I mean, the LMP comes from an auction between generators. Not if you let the loads come in, that could really be. Maybe that'd be a little weird, But I don't know. I don't know about that. But we've got a service, and we had supplied. Why would we discriminate against loads compared to generators? So that'd be a bit strange. All right, you still awake? Okay. So here's the outcome of this. Eninox, so one of you, oh, you're not here, one of you interviewed on Tuesday for Eninox. This company took off after FERC 745 came in. They were a little company, and wham, they, I don't know how much they're worth today, but it must be billions.
They're a demand response provider.
Yeah, they get commercial buildings together to be able to aggregate commercial buildings to provide these megawatts, it's often called, and they work with all sorts of different levels and trying to get contracts in place with loads and contracts with utility companies, and basically act as virtual generators, and they're an awesome company, and they have estimates. This is old data, but they claim to have 20 billion tons of CO2 saved and all this stuff. This is definitely old data. I don't know this $1 billion in dollars saved. But the big thing was last year. So it was winter 2014, the polar vortex. Must be, January 2014. So the U.S. So the ISOs claim that they would have been massive blackouts without FERC Order 745. Because what happened was the natural gas couldn't be transported where it was needed. There's a complete blockage of natural gas to most of PJM, to Texas, and so they just had a loss of resources for days at a time. And so they were able to do this. They were able to get consumers to shut down and keep the grid going. So PJM, the prices went to $1,800 a megawatt hour, which PJM doesn't see that much. That's that's amazing. And they claim that they were able to deal with this all-time peak of. There was two things going on. There was a peak of generation as well because of the cold weather, electric heating. And they had no reliability issues. And I know Terry Boston, the CEO. He says it would have been over, and I really believe him that they would have had a blackout. What's the marginal value of PJM? Imagine if you didn't have this. The whole East would have gone black. You're talking about $500 billion. It's a meaningless thing. And then the same thing Texas says this as well. So ERCOT says that they would have blacked out as well if they couldn't have shed load. And they need the contracts in place in advance. You can't. You need to have negotiations, and hey, we'll pay you this much, and you'll agree to do this. And they must have some rules to avoid that. I don't know how they do it. I don't understand it. Okay, so it's been an incredible success story, but the generators moved in and lobbied and lobbied and lobbied to fight this. So it was a blazing success. And I jumped ahead of myself. You know the punchline anyway. But so what happened is I forgot the EPA, electric power. I'll send it all to you. So a lobbying group came in and brought in all the energy economists they could, including Bill Hogan from Harvard, and argued to a local, not the Supreme Court, to a lower court, that number one, it's a double payment. That this is an arbitrary payment to consumers. It's a double payment, they called it, and that's that arbitrariness, it should be struck down. Number two, states' rights. This is interfering with the retail markets, and therefore that's not the jurisdiction of FERC. And so they spent a fortune. I'd love to see the consulting checks from Bill Hogan at Stanford. Standing up before court and saying, yes, it's a double payment. Here's marginal cost. Here's marginal value. The price should be X. So it died. They were successful. They would convince the lower court that it was. It was gone. But I claim there's no way this could survive. And if this is upheld, it's going to die. And you all know why, don't you? Can you read my mind? Not you, Joel. You know, you've seen this. You know why it's absurd to you? Okay, suppose it's a success, okay? So you've seen the price maps in Texas, right? You know, you get $9,000 a megawatt hour, and then it's negative over here. And in MISO, it's happening all the time. You've got these huge prices. So what if it worked? So ENERNOC comes into every state in the US. They set everything up. They've got, you know, every single building, commercial building, when the price gets high, wham, the energy consumption in HVAC goes down 10%. You know, what would happen? Peaks would be shaved, because a peak would come, we'd all reduce our power, no peak. Contingencies, whack, they're gone, you know. I mean, you know, there might be some replacements that would have to come in, but wham, you know, there's a fault, loads can, any rate you want, we can do it. The right engineering, you know, how do you want this? You want this shape? And we'll see it in this course. I mean, you want this shape or this shape, loads will do it. You know, engineers, we can do anything. Really, I mean, I'm not kidding. So prices, it moves to the marginal cost. It's the absolute nirvana of any economist in power. Nirvana is achieved, right? Now, come on, now you must get the joke.
You were talking about earlier, right? Like shedding load for different buildings or different groups would be, they're not equal pricing.
Well, no. The thing is that I'm talking about under this order. So this way of incentivizing consumers, okay? And, you know, we'll see through engineering, we can do anything with loads. So if you look at, like, during the times that so during the polar vortex, you know, there might have been a peak like that because people came home, turned on electric heaters, or their house was freezing. Man, we could easily do that, you know, with loads. You know, basically preheat, you know, and then let the place get a little cooler, and then reheat a bit. No problem. I mean, Jesus, we can do this. So in terms of engineering, we can get rid of that. We can do it. No problem. Okay, so we'll get rid of the peaks. The contingency, same sort of thing. We can smooth it out with loads. And so the prices will be smooth to that light blue color in Texas, or light blue colored MISO, which is maybe a little higher than the marginal cost, but basically the marginal cost, which is the dream of any economist. But come on.
That's not up to the consumer, though.
What?
That's not up to the consumer.
No, so we couldn't do it. No, this would be the load today, like during the polar vortex when there was a huge demand, say when people got home. But we can do this through engineering. We can put in control systems in commercial buildings and have them, you know, control so that the temperature is within strict bands and the load is shaped. I mean, we can do wonderful things with control. Well, we should. We'll have to find out why.
It's just not.
There's no market model. There's no opportunity without crisis. See, if we were successful, then we're broke. If we achieved the nirvana, then we've made the price marginal cost. If the price is marginal cost, we never make any money. It's completely circular. Right?
So that's why you're saying it's short term.
It's idiotic. I could never get an investor. So I know I could do this, okay? As an engineer, I could do this, and I know it, okay? If I took this to an investor, the investor would take 10 minutes to say, well, if you're so successful, you'll destroy your market. You will you'll smooth the prices, and you'll put yourself out of business. There's no way you can make money without crisis. And that's what the generating companies who lobbied to get rid of FERC 745 knew. That if you make this successful, you'll drive them out of business because they make money from crisis. Those prices go up, you know, to a few $100 a megawatt hour for a few hours. They've made their money for the month. and you get rid of that, what are they going to do? If you flatten those prices, every generator in the U.S. is out of business. You know, and also everybody who's providing these ancillary service. So the Supreme Court is deciding the case right now, and I'm so sad. It's awful news. I'll tell you. Yes, me. No, I'll tell you.
Wouldn't it be possible that maybe let's catch it and then restabilize and recognize and we could pay a little more? I can't quite see if you're for or against it.
Well, FERC Order 745 is the most naive thing I've ever seen in my life. It is absolutely silly, because it is true that if anyone thinking about this for a little while would see prices will never get high again, and therefore ENERNOC no longer has a business case. Now, ENERNOC the thing is, you could say, well, why is there ENERNOC yet? Well, it is true that business people know you make money through transients. You don't, Apple makes a fortune, their Apple Watch for a while, then nobody cares about it for a while. It's through transients. So ENERNOC is going to make a fortune for a while, but then they go out of business, and that's it. They walk away to something else.
When demand response is being applied, they could add to the marginal cost.
Well, there's a million ways of doing it right. We'll talk about that. There's a million ways you could make a sustainable model for this. But this particular model based on locational marginal prices is no good for demand response, and it's no good for generators. It puts everyone out of business. It doesn't take into account that to do this would require a big sunk cost. I'd have to go around to every commercial building in Florida and modify the building automation system in the buildings. That would cost maybe a few $100 per building, maybe $1,000 per building once, and never again. And the same with generation. It doesn't take into account any of the big sunk cost issues. But yeah, we'll talk about how to do it right. I mean, there are other models. In fact, there's another FERC Order 755 where they did do it right. They came up with something sustainable, which is pretty cool. And we'll talk about that a bit later. But guess what they're saying right now? So here's a remarkable thing. So the lower court struck down FERC Order 745. On what reason? So there are two reasons brought to the court. One was state jurisdiction, and one was the crazy prices. And the double payment, though, not the crazy prices I'm saying, the fact that you're double paying consumers. Well, it was struck down only based on state jurisdiction. And my dream was, and so the Supreme Court agreed to take the case, but they took it based on both of those counts, state jurisdiction and arbitrary prices. The Supreme Court doesn't do that. The Supreme Court's supposed to review a case based on the reasons it was rejected. They don't make up their own reasons, but they arbitrarily decided to choose to review it based on the two initial arguments, which is some really strange thing. It must have, who knows the motivation? But so as of now, as of today, it's mainly Scalia who's talking, and they're focusing mostly on the state jurisdiction issues. And so it's possible it could get struck down on state jurisdiction. If that happens, that's the end of everything. I mean, everything, because if FERC Order 745 is not constitutional based on state versus federal jurisdiction, then all the other programs that are around will be gone as well. I mean, it would just completely disrupt the whole energy industry. Now, they must know that, so maybe they won't do it. But the trouble is you've got some real activist judges who might do something crazy like that. But tomorrow they might talk more about prices. So another scary thing is Alito recused himself. So there's an even number of judges. So there could be a tie. And you know what happens if there's a tie at the Supreme Court? The dismissal holds. So if it's a tie, then we lose that FERC 745.
That will still not be the state rights compromise, right?
Yeah, the state rights would be a disaster. Absolutely. No. It could be a tie based on states. It would be states' rights because it was rejected based on states' jurisdiction. It would stand based on states' jurisdiction, and that means all sorts of other things would be challenged based on states' jurisdiction. It'll be unbelievable next few years.
Retroactive order on them.
No, everyone will sue. So all these power companies that feel like they're being challenged by other FERC orders are going to come in and say, you said that states' jurisdiction applied here, it applies here as well. So
They can pretty much, if they go to the right state, they can do whatever they want.
no, it's mainly that there's other FERC orders that are really valuable. They could get struck down. And they sort of grew in these incentives for some fantastic programs. It's also...
You're saying that if this Supreme Court decision gets dismissed, right, then it's up to the
if it's a tie,
It's tied.
then the lower court's decision is upheld.
Right.
And that was based on states' jurisdiction, which is the worst thing that can happen because we want FERC to be able to regulate these things because if an issue in Connecticut affects Florida, it is a federal issue. I mean, security of the grid is a federal issue. To pretend it's a state issue is nuts.
What I'm saying is, so if they do tie,
Yeah.
it's up to the state's jurisdiction. Potentially, a utility company can go into a state where it's very deregulated, and pretty much just control it.
I don't think that's the issue. You see, they can't already. Now, the real issue is that other orders will be struck down. FERC will lose a lot of their incentives today because already there's it just limits people more because already there's ISOs are very limited what they can do. So just limit them more.
Yeah, even the Clean Power Act can.
Yeah, everything. Yes, they'll go right to the Clean Power Act. Yeah. Oh, yeah.
So is it basically like the utility companies can now be like, oh, this is a states' rights issue, so you can't actually tell me to do this, so I'm just not going to do it because it costs me money or something like that?
Yeah, well, all of this applies to the ISOs and who they can engage in the markets. And so this would say that these are like contingency reserves. If there's another FERC order for like regulation reserves, that would be gone like that. Because the gas generators would love to be the sole providers of that and not have to compete with battery companies. So where that would go. The Clean Power Act, all these things that come from the federal government would come. But my dream is for it to be struck down, but based on the ridiculous arbitrary pricing. That's my dream. It's unlikely, but that would be awesome because then FERC would come up with a new order which would be more flexible. So different ISOs could experiment with different pricing strategies, and you might there could be some experimentation to come up with something that works. For FERC to give something so specific on how to deal with loads, that's what to me is like, wacko, just completely wacko. So I convinced you I kind of believed it. I don't. I think it's completely nuts. I think it's, and exactly because I call this the ERCOT nirvana. If you made Texas completely light blue, the economists initially would be thrilled. And then it would turn bright red when everybody went out of business.
At the same time, the argument for competitive equilibrium theory was that the price is converged.
This is the hilarious contradiction that the dream is price should go to marginal cost. And this says that yes, the dream is achieved. You're all right. We achieved the dream, and it means everyone's out of business. It's just.
It's like wishful thinking because if that was true, if no one wanted to make a profit.
Yeah. Well, the thing is that I could never get a loan for a business because anybody looking at this for 10 seconds would know that I'm going to go out of business.
If you had a dictator.
No, you could come up with good rules. You see, we're going to look at some good rules. There are ways to make this work.
Well, technically.
Yeah.
It's kind of like if you had like this generator that was already paid off and you didn't actually need to make a profit or anything, then it would still be in business. But if you need to start up a new generator for any reason because the amount to produce power is the same as the amount to...
Well, the main thing is you wouldn't get any investment in anything, in research, in new generation, but also there's sunk costs. There are people that run these generators, and big repairs that have nothing with marginal cost. There's sunk costs that have nothing, and so, you know, if the prices really stayed at $20 a megawatt hour, then everyone would go out of business.
So
you know.
labor is not included in margin?
No, it's not. No, because it's a fixed cost. You know, the number of people there working.
So that would just
yeah.
be the A.
Yeah, that's the A. Yeah, that's the A exactly. The B is just fuel cost, really. Yeah, it's just it's really wild. But I mean, I can say it real fast. We'll get into this more later. But like the kind of things that work are contracts for services. You know, if I want this place clean, I don't have an emergency auction whenever it gets dirty. You know, I have a contract. It's I'm gonna. You have to give me 2 weeks notice if you're going to quit. I have to give you 6 months notice. I'm going to fire you. And you're going to come every day and work for 8 hours. And you know, the same thing here. You know, I'm going to give you so much money for services, and I'll pay. And in this case, I can pay you more if you deliver more services, and less if you give it less. And those contracts can be negotiated. There'll be some arbitrariness to them, just like there's arbitrariness to wages today, right? I mean, it's just a magic value in your salary. It's pretty arbitrary, you know. And so things like that exist in the power markets today, incredibly successful, and that's what should be done. You know, that would be fantastic. And so I've convinced that, you know, people in the ISOs that's true. You know, I mean, they would lobby for that as well, like Terry Boston at PJM or Steve Whitley in New York ISO. They're on board that this is a bad model. You know, and they've all seen this talk. And this is from a lecture last year. But okay, so anyway, that's just a brief detour because you do need to know what's going on in the news right now, and we'll come back to this actually in a few weeks to this and some of this stuff.